Many thanks, Professor, for your introduction. So today I would like to show you some of the preliminary results that we obtained within the framework of the STRIPES project, which was funded by the last spring PNRR 2022 call, in which basically both University of Calabria and...
So, it's better to speak in Italian. It's a problem for you, or?
It's better in English.
It's better in English. Okay, let's go.
And University of Salerno are focusing on the development of an eco-friendly FRCM for structural application. In these first stages, our colleague from material engineering, Professor Sebastiano Candamano, is working on this task. Unfortunately, he was not able to attend the conference. Well, I will do my best to try to replace him. So, this is the outline of the presentation. I will start with a brief introduction of the potential of alkali-activated material for civil engineering application. Then I will describe the material that are involved within the several mixed designs that were evaluated, and then the methodology that we follow to characterize the mortar. Experimental results, and I will finish with some concluding remarks. As you know, cementitious materials are widely used in construction industry, and this is for several reasons: the good mechanical properties, the good durability, and also a relatively low cost. However, although these advantages, there are still some concern regarding the environmental impact of this material. In fact, we know that cement is mostly produced by clinker that comes from the extraction of clay and limestone, and this, during the process of heating the clinker within the kiln, it occurs a process called decarbonation, which releases a significant amount of CO2. In addition, limestone and clay, due to their extraction, contribute to the soil degradation and also a loss of biodiversity. So to this end, it can be said that cement production is almost responsible for almost 7-8% of the global CO2 emission. In this context, it is crucial for the construction industry to find some both alternative material and system to reduce environmental impact of cement-based material. In this context, alkali-activated material seems to present some potential in this regard. In fact, they are produced by reacting aluminosilicate-rich material, for instance, fly ash, slag, or metakaolin, with alkaline activators. And apart of the advantages related to the good mechanical properties and durability, there are also some environmental advantages that can be useful for construction application. For instance, the reduction of the CO2 emission. In fact, they do not require high temperature clinker burning. The use of industrial waste, because for instance, both slag and fly ash are industrial byproducts, and also a lower energy consumption because they don't need a high temperature kilning for clinker production. In this context, our objective was to develop an alkali-activated FRCM for structural application. Here, in this slide, I just reported the raw material that were involved during the experimental campaign. As a reactive powder, we consider both slag and fly ash. As alkaline activators, we considered potassium hydroxide, sodium metasilicate, and sodium carbonate. And finally, sand. It is worth mentioning that the water reactive powder was set as 0.56 and the sand reactive powder was set as 0.23. Here, basically, we can see that we produced 8 different mixtures with a mixture that can be mainly divided within 3 subsets. The first subset, in which has a reactive powder, we can see only slag, and has alkaline activators, we can see both sodium metasilicate and sodium carbonate. The differences among the different mixtures basically correspond to the different ratio between the sodium metasilicate and the sodium carbonate, which is basically set to 3,1, 1,1, and 1,3. Then we can see the second subset. Here they can be considered sort of, let's say, hybrid alkali-activated mortar due to the fact that they contain both slag and fly ash as a reactive powder. And here the difference again among the different mixture correspond to the different ratio between the sodium carbonate and the sodium metasilicate, which was always set as 3,1, 1,1, and 1,3. And the final subset, here we replace the sodium carbonate with potassium hydroxide, while the ratio between the slag and fly ash was kept constant. After doing this, we started to think about what kind of test we can do to characterize this mortar. Regarding this aspect, here I just reported some of the tests that were performed. Some other tests are being performing in this period. Regarding the mechanical test, we performed X-ray diffraction test to characterize the several phases that belong to the mortar. Regarding the physical properties, both spreading test and capillarity absorption test were performed. And finally, mechanical test, we evaluated the compressive and flexural properties of the mortar in the hardened state, and also pull-off test to evaluate the bond between the mortar and the substrate. Starting with the result and with the XRD test, here from the result we could see that the main phases that can, at both 2 and 28 days, correspond to the hydrotol seat and CASH gel, which basically belong to the reaction between the slag and the alkali activators. Then we can also see the presence of molite and silica, which are mainly some impurities which belong to the raw powders. And from this plot, some other conclusion that can be drawn is the fact that with the increase in the sodium metasilicate, the peaks, as can be seen in the plot, become more intense at both 2 and 20 days of curing. And this can be mainly associated to the higher initial basicity, which is produced in the mixture, which accelerates the dissolution and the reaction of both reactive powder. Then, regarding the spreading test, well, this is an aspect that is being still evaluated, because as you can see from this plot on the left, we see that the spreading of the mortar was relatively high, most of the case higher than 20 centimeters, and in particular we can see that the addition of fly ash led to have a more fluid mortar. In this regard, what is being done in the last weeks, we are trying to add some thixotropic additives to improve this aspect, because for FRCM application we would prefer to have, well, let's say thixotropic behavior. Moving to the capillarity absorption test, what can be seen from this slide is that basically, as you can see from the table, the mortar with the lowest capillarity absorption are those containing the highest amount of sodium metasilicate. The reason for this can be mainly attributable to the fact that increasing the amount of sodium metasilicate led to a higher production of CASH gel, and as a consequence the mortar start to become more let's say more dense, more compact, with less pores and fewer pores. Moving to the mechanical part, and starting with the compressive and flexural test, here it can be seen that among the different mixer, especially for the mechanical properties of the mortar tested after 2 days of curing, the mechanical properties were relatively low. And this, just to remind you, correspond to the mortar in which there is the lowest percentage of metasilicate and the highest percentage of sodium carbonate. The reason for this can be mainly due to the fact that the calcium carbonate has a low ability in activate the reactive powders, especially a short period, even in the presence of the sodium silicate. From the other results, what we can say is that basically for all the tested specimen, in general, the mechanical strengths are higher in the mixture which contain only fly ash. And this is due to the fact that the fly ash contain less calcium and is mainly composed of aluminosilicate, which require a higher pH to activate. After this, we wanted to understand if this product that we are developing were comparable with what's available in the market. And except for mortar 1 and mortar 4, we can see that the flexural and compressive properties of the mortar are relatively good for let's say, structural application, because, just to remind, they were compared with mortar typically used for FRCM used to strengthen masonry. After that, we also evaluated the mechanical properties under sulfate attack. In particular, the material was exposed to a 3% of magnesium sulfate solution for 60 days. Here you see properties also at 30 days, because it's the age in which we renew the solution. And from this test, it can be seen that the reduction doesn't seem so drastic. However, these were the last tests that we performed, and few specimens were tested, so further investigation are needed to compare these results. Another aspect that was evaluated was the bond between the mortar and the substrate. In particular, as I will explain later, we evaluated the bond on two different substrates, both masonry made from tuff and from bricks. And in general, it can be seen from the test that the bond strength was relatively good, highlighting the potential of the FRCM, of this mortar for FRCM application. Now, just to conclude, let me just show you an overview of the project, so where we are, where we want to go. We are now working on task 1 and task 2, in which we can see the mixed design optimization, some of the results that we see in this presentation, and also the characterization of commercial FRCM system. Regarding this aspect, what we are performing are basically tests on the FRCM constituent material, namely tensile test on the fiber, compressive and flexural strength test on the mortar, tensile test on the FRCM, and also bond test, performed on both masonry made from brick and tuff. In task 3, what will be done is basically the test on the same FRCM system, but considering the eco-friendly mortar developed in the project. We will also evaluate some aspects regarding the durability, so both under elevated temperature and under freeze and thaw cycle. And finally, we will evaluate the structural response of strengthened masonry elements. And regarding this aspect, we will perform both compression tests on masonry column strengthened with both commercial and eco-friendly FRCM, and also a shear compression test performed on masonry wall strengthened with both two systems. In conclusion, what we can see from the results that we just observed is that the presence of fly ash increases the workability of the mortar. The reactive system with higher sodium carbonate content show low initial reactivity and moderate performance up to 20 days of aging. Despite being a stronger activator than calcium carbonate, only the addition of appropriate quantity of metasilicate improves the mechanical performance, especially at short aging times. There were no significant signs of deterioration regarding the behavior and the sulfite attack, and also the bond between the mortar and the substrate seems to highlight a good potential for FRCM application. So, thanks for your attention.